Welcome, everyone. Thank you for joining us for the iSamples 2015 Fall Webinar Series. iSamples, which stands for the Internet of Samples in the Earth Sciences, is an EarthCube NSF-funded research coordination network that seeks to dramatically improve the discovery, access, sharing, analysis, and curation of physical samples and the data generated by their study for the benefit of science and society. Our first speaker, Jim Bowring of the College of Charleston, will speak about advanced cyber infrastructure for geochronology as a collaborative endeavor. Our second speaker will be Chris Lenhardt of the Renaissance Computing Institute, who will speak about the cyber infrastructure for physical samples, synthesizing related efforts, and the development of the Internet of Samples. The format of these webinars will be such that each presenter will speak for 20 minutes, and then there will be 10 minutes at the end of each presentation for questions. If you have questions, please type them into the chat box during the presentation or afterwards. No question is too small. We invite as many questions as possible. Jim, we will begin with you. I will pass the screen sharing to you. Actually, you already have it, so you may begin when you are ready. And I will unmute you first.
Thank you, Megan. Good afternoon, all. I want to take one moment and acknowledge that today is Veterans Day. And it's supposed to be a celebration day. My first slide here is the roadmap for the talk. I want to give a little bit of my background, talk about cyber infrastructure for science, the Earth Time Initiative, my research lab, CERTLS. I'll explain that shortly, and finish with some thoughts and questions. I teach at the College of Charleston, which is a primarily undergraduate institution with 10,000 students. I teach software design, engineering, and testing, and I'm the PI of CERTLS, which stands for the Cyber Infrastructure Research and Development Lab for the Earth Sciences. I'm also a collaborator with the National Science Foundation-funded Earth Time Initiative and an active participant in EarthCube, currently serving on a role in the governance structure with Lee Allison. I've been collaborating with geoscientists for over 20 years to build cyber infrastructure to support their science workflows from cradle to tomb, as we say, or from field to public archive. And I've been developing a working definition of cyber infrastructure for science that I find useful, and you may as well. That it is a collaboratively and sustainably evolving socio-technical system of systems, including humans, software, computing devices, and electronic storage intended to support and advance science and ensure reproducibility. It's important to understand that cyber infrastructure for science is not static because it includes human stakeholders and they drive its evolution. I've come to this understanding through years of experience as an initially unwitting player in the creation of a cyber infrastructure system. This image is of Charleston's Ravenel Bridge, the longest cable stay bridge in North America, and it serves, along with the also shown trestle bridge that it replaced, as a metaphor for cyber infrastructure supporting human workflows. Plus, it's quite beautiful. My brother, Sam Bowring from MIT's Department of Earth and Atmospheric Sciences, realized in the 1990s that scientists writing software to support their science was probably a dead-end endeavor, and he enlisted me as a computer scientist and software engineer to work with him and his students to explore collaborative development of sustainable, domain-specific, in his case, geochronology, software solutions. The bulk of the software used at that time in SAM's and similar geochronology labs was Excel-based, somewhat closed source, incompatible with later Windows operating systems, and sporadically maintained. This specific issue of software sustainability, I want to note, keeping systems up to date, has come to be really at the heart of any cyber infrastructure discussion. Initially, we had no notions of cyber infrastructure. The term wasn't in our active vocabulary. Our first solutions were as simple as automating data transmission between machines, which was being done by hand, with students reading data from a printout and typing it into another application. In the early 2000s, Sam and his colleagues founded the NSF-funded Earth Time Initiative, with the goal of calibrating Earth history and developing the geochronological techniques necessary to produce high-precision dates. Earth Time also recognized the need for robust open-source software to support data reduction, analysis, and archiving. Note that this is before EarthCube or NSF's 21st century vision of cyberinfrastructure. Our first collaborative software development effort within Earth Time was the program Tripoli, which was designed to process thermal ionization mass spectrometry, or TIMS, uranium-lead raw data. Tripoli imports raw mass spectrometer data files and supports interactive review and archiving of isotopic data. It facilitates visualization of temporal trends and scatter used during measurement, statistically rigorous filtering of data, and calculation of statistical parameters. It has become a workhorse for the TIMS community. During this development of Tripoli, we unwittingly entered into cyber infrastructure development and evolution as we realized there was a possibility to use the internet, which we now know as the cloud, to establish and maintain models and instances of commonly used parameters as well as analytical results. The first candidates were the so-called physical constants, including decay constants and the Earth Time certified tracers or spikes used in geochronology. We developed an architecture that provided standard schemas so that users of Tripoli could create, store, and share version models of their parameters and results. Another of Sam's goals for Earth Time was to find and eliminate the sources of interlaboratory biases. Leveraging our experience with Tripoli, his dream was that we would, I just lost my place here. Leveraging our experience with Tripoli, his dream was that we might develop a gold standard open source software system to extend well beyond Tripoli and automate the complete workflows of geochronologists with improved statistical techniques and new algorithms for propagating uncertainty. He imagined that in this gold standard could be used to eliminate sources of uncertainty due to software in these interlaboratory comparisons. Earth Time had requirements for such a system that included the following: that the applications be open source and provide for real-time interactive data reduction and uncertainty propagation, that they be extensible with plug-and-play models, that to be interactive graphical and statistical tools, that the software and systems could produce publication-ready artifacts, that they could automatically capture metadata, and that there would be the production of a standardized and extensible record for transport to and from archival databases. Sam enlisted Doug Walker of the University of Kansas Geology Department, who does TIMS geochronology, and who was using Tripoli and knew the benefits of this new approach. Furthermore, Doug was actively engaged in the creation of online repositories for archiving geochronology data and analyses in the geochron.org repository that was part of EarthChem. Doug introduced us to CSAR and IGSNs, and we incorporated them into the workflow automation at an early date. More on this later. Doug provided me with initial funding to explore and prototype these ideas, and I founded the Cyber Infrastructure Research and Development Lab for the Earth Sciences at the College of Charleston that I mentioned earlier in 2006 to expand this collaboration and to engage undergraduates in the effort. This gold standard software system we named initially UPB, Uranium Lead Redux, and now it's known as ET for Earth Time Redux, ET Redux. However, it took many years to move from the prototypes to a working system because in addition to the complicated nature of the workflow and mathematics, there were many cultural differences between computer science and geoscience that emerged. At the simplest level, there was a difference between zero-based and one-based indexing of matrices. At the hardest level was learning to see what the world as the other domain did. Some practical cyber infrastructure solutions emerged in the form of a common language, complete with dictionary, visualizations, process maps, and prototypes. Along the way, we discovered how to conduct collaborative domain-specific software engineering. The main attribute of this process has become its iterative nature and the management of continuous change. My main collaborator was and is Noah McLean, now at the University of Kansas, and he and his colleagues and I and my colleagues have communicated weekly, if not daily, via all manner of media for the better part of 10 years, as ET Redux has evolved and gone into production science. The architecture of the system was established early, and as you can see, includes both CSAR and Geochron.org. It is centered around the sample, in the case of geochronologists, a rock sample, and you can see immediately that the lower left arrow leading from the sample goes direct to CSAR for the ingestion of metadata and the assigning of an IGSN. We did this early, and we've done it continuously. And UPB Redux in this drawing, and what's now known as ET Redux, performs several roles. One role is as a workflow manager. Another role is as doing analysis. And the third role is this compilation mode. And compilation mode was an idea that we toyed with initially and didn't realize the power of, and it turns out to be one of the most used and powerful aspects of UPB Redux or ET Redux. What we have developed here is what we call archiving with a click. And that means that from within ET Redux, the scientist can, at any time during the analysis, during the process, archive the results privately or publicly, think of as a cloud-based storage solution, and then reopen it and continue, override the previous saved state with a new saved state until they're finally ready to make it public and publish it and get a DOI. This ET Redux was the first system and one of the few existing to support automation of field to archive workflows and to incorporate the use of IGSNs. So as an example of how the compilation mode works, I'm going to bring some slides from Doug Walker. The next few slides show ET Redux at work doing compilation with some of his files. I've got to click the right button here. So this is one of the screenshots where the user is able to interact with, here you can see the Geochron database. You have to have, possibly have to use your Geochron credentials depending on whether it's a public or private data set. And here he's going to combine a volcanic and a related Pluton data set that have previously been processed by ET Redux, archived at geochron.org, and now are available for downloading via the use of solely their IGSNs. And here's two of them here, both with Douglas Walker as the preface to the IGSN. And this shot here shows a compiled Concordia plot that is composed of these two downloaded records. And you can see in the next slide and the slide following, in this case, the volcanic sample as it was processed during using ET Redux, and the related Pluton as it was processed using ET Redux. In each case, the data and results were uploaded automatically to Geochron, and then in this compilation mode, they were retrieved, and it's possible to retrieve any number of analyses and view them and analyze them in this mode. So this, as I said, this was an experimental mode that we created, and it has turned out to be a very powerful and highly used mode for ET Redux. So, evolution, as in evolving cyber infrastructure, as in the changes that have happened over the years with this collaborative effort among CERTLS, MyLab, and EarthTime and EarthChem, and Geochron.org. We've had two major grants, both NSF 3-year grants, one for laser ablation inductively coupled plasma mass spectrometry to build on the work we did for TIMS. And again, the software works in exactly the same way. The source of the data is obviously different, but the processing architecture is basically the same. And we're now currently in the beginning of a 3-year grant for DIBS, which is data infrastructure building blocks. And in this case, we're dealing with uranium series data from coral in the ocean. And we're extending this architecture to include the processing of uranium, thorium, and other uranium series isotopes. Again, leveraging what we've already built, so that doesn't have to be invented again. And that was part of the whole idea of developing an extensible architecture, was that this exact case could happen where we're able to extend it easily and powerfully. So the ET Redux has been adopted heavily in the TIMS world, and we're now starting to have it used in the LAICPMS world. We have over 160 references in major journals for papers that refer to this ET Redux and its development. We've also had synergistic opportunities with EarthCube. Obviously, iSamples is one of them, and I'll talk about that again in a minute. But we've been able to serve as an exemplar, as I said previously, of working cyber infrastructure that scientists, field scientists, or long-tail scientists, however we call them these days, actually use and depend on to conduct their science and publish their results. And that's, to us, a powerful statement of our viability. So under continued collaborative development, ET Redux is continuously developed, again, in the same model that we've used over the last 10 years with daily or weekly meetings and feedback and playing with prototype solutions, et cetera. We've also spun off a couple other products. One is Chrony, which is almost done. It is a mobile app for Android and soon for Apple iOS that allows a user to, using ET Redux, build some custom views of the data tables and then port them to their mobile phone or tablet and use that device to query using IGSNs only, the Geochron database, and view in the field the data table in Concordia and other graphical products of ET Redux that are stored on Geochron. So we hope that this becomes a useful field tool for geoscientists, and you'll see in the latest edition of EOS that another effort of EarthCube, the EC3, can't remember what it stands for, but Maddie Muhuki from Sonoma State was featured on the front talking about the merging of cyber science and earth science and the evolution of field tools. So hopefully Chrony will join that set of tools. Topsoil is another spin-off which you may have heard of. We presented it at AGU last year. It's an anagram of Isoplot, which was developed by Ken Ludwig and is depended on around the world in educational instances as well as universities and industry for visualization of geochronological data. But he's retired, he no longer supports it. It doesn't run on modern Windows systems very well. It's written in Excel. And so the community came to us and asked us as Cirtles to see about maybe starting an effort to replace it. So we've mounted an open source community collaborative effort on GitHub to replace it, and have been making enough progress that we've got people involved in the development and actually using it now to do some publication of artifacts. And finally, we get to Mars here, which we'll talk about in more detail in the next slide, which stands for the middleware for assisting with registration of samples. And this is the specific tie here to iSamples, where we hope to leverage what we've learned over these years to help solve some of the problems with a growing and volume of data being ingested into CSAR and the IGSN system. So I attended the iSamples RCN workshop in Austin last year and became part of a working group 4, along with a person named Alex Angstfer, who's the Geological Collections Manager at the Scripps Institution of Oceanography. She's in charge of getting IGSNs assigned to all of the Scripps legacy and new samples, quite a daunting task. Not much happened, though, with the working group until we met at the EarthCube All Hands meeting in Washington, and Alex and I decided to explore the idea of jump-starting something here and using her tech as a use case study for automating the acquisition of IGSNs from CSAR and the uploading of metadata. Scripps has thousands of core samples in need of registration, and the current process involves Alex manipulating Excel spreadsheets for upload to a holding bin where somebody at CSAR, I think it's Megan, vets them. So this use case study involves understanding what is needed to process a large volume of a specific kind of sample as a way to understand the underlying issues. I've been in many discussions, and this is, I want to make a point here, in EarthCube workshops and elsewhere, where the quality of data, hang on one sec here, I just had a Hangout pop up, I don't know how to get rid of it. Does that show on the screen? No, good, okay.
No.
I've been in many discussions in EarthCube workshops and elsewhere where the quality of data ingested into archives is a concern. And I take the position, along with others, that because of the volume of data, we just need to forget about humans vetting quality on the way in, the quality of data on the way in, and realize that this is big data and that the statistical tools of big data are up to the task of automating this quality vetting process. The working group has met several times to explore this use case. It is now to the point where we are mapping the standard Scripps fields to the CSAR metadata fields, and along the way we have discovered gaps in our knowledge and in the data, including the specifics of the datum used to specify the lat-long entries in the Scripps database. I have volunteered to kickstart development of the prototype named Mars, as I just mentioned, middleware for assisting with registration of samples within my undergraduate lab, online at github.com, as an experiment in sustainably building a solution for this case study. Imagine that a typical use of Mars would be as a graphical user interface that assists a user to pull in their primary data store and use it to build metadata profiles for samples on CSAR with interactive and constrained lists for various fields, and then to assign and get IGSNs and record them into the data source used. We hope to learn not only how to automate the specific process for the Scripps cores, but more general lessons on how to extend the system and gain community collaboration in the process. For example, we've already discovered a shortcoming in available scientific software. It turns out that there does not exist, to our knowledge, a robust system, either as an application, or a web service for reliably converting locations among datum, including UTM. One of my students is taking this on as a research project. The mathematics exists, and there are sporadic solutions out there, but none of them are robust in terms of performance. There are likely many other small gaps that we'll need to be filling as this process evolves. So, thoughts. Cyberinfrastructure for science, you'll see here and on the first slide that I have 4 in parentheses, and that's because I'm starting to think that we need something called cyberinfrastructure science that will solve a problem of the siloing of, in academia, of various fields by bringing together as a giant silo, various domain-specific sciences, computer science, possibly social sciences, et cetera, and as a way to organize our thoughts about how cyber infrastructure is going to continue to evolve for the sciences. Remember, we want to support reproducibility in the long run and sustainability, and to learn maybe how we're going to manage the continuous change that is inevitable as a result of humans being in the mix. And so back to my working definition of cyber infrastructure as a collaboratively and sustainably evolving socio-technical system of systems, including humans, software, computing devices, and electronic storage, intended to support and advance science and ensure reproducibility. So I'm open to questions.
Thank you very much, Jim. Just a reminder to everyone, please put questions into the chat box, and we already have some here, so I'll start with those. Jim, how could these systems that you described be scaled to other analytical techniques?
So the question is about the architecture for ET Redux, I'm assuming for the geochronology, as
yes,
opposed to what
you can refer to either that or
Mars. Each case is going to be different, right? At the high level, what we've got here is an architecture that depends upon modularization, right? And so this is one of the key concepts that allows this to be borrowed and extended to serve other uses. The modularization, that is, that data transfers between stages inside of the process in standardized formats. We use something called extensible markup language, XML, and it has schemas controlling the shape of those documents. But by having modularization and then this notion of plug and play in terms of algorithms, we're able to manipulate this architecture to some extent to solve other problems. Obviously, outside of geochronology, the lessons learned and the borrowing from this are going to be at a higher level because this is the visualizations, et cetera, are so far defined within the geology's domain. Hopefully that answers your question.
Great. Based on your experiences, Jim, what are your top 1 or 2 lessons learned for developing cyber infrastructure for science? And similarly, what are the biggest challenges that you've encountered?
So, lessons learned and challenges, is that the question?
Yes.
I can't see the ticker.
Yeah, it was a private question.
Okay, so the lessons learned here are that this is a collaborative effort between or among groups of people that have possibly initially a hard time communicating, right, in terms of science. We have different vocabularies, different understandings, different assumptions, different sets of words, different sets of mnemonics, et cetera. I mean, it's just enough to drive you nuts. I've been doing this a long time, and it's taken a long time to get to the point where we're all comfortable. So that was actually an eye-opening lesson learned. I didn't really expect that to be that difficult. On the other hand, the rewards of doing that are also remarkable because we have created software that people basically would be very unhappy if they couldn't use it. So they enjoy using it. They've contributed to how it's designed and how it works. And so that's another unintended consequence in the sense that there's real adoption and real demand for this stuff. I also didn't quite anticipate that. I think have I addressed the question?
Yes, I believe so. And
okay.
Finally, one last question, Jim. Do you know how far the IGSNs have been implemented into sample collection workflows specifically for geochronologists in the field?
In the field, I have no knowledge. Okay. So this is obviously a place that work needs to be done. We talked about it at the iSamples workshop, but we haven't been addressing it.
And similarly, do you know how far IGSNs have been used in the literature for geochronologists?
IGSNs are now being used in the literature because those scientists that are using geochron.org, for example, are able to get DOIs for their data sets and then publish them. And this has happened. Noah McLean, for example, my collaborator, has done this, and others as well. In fact, we learn whenever something breaks at CSAR, I find out because somebody's trying to publish something. And so we've built into the system, interactions with CSAR and IGSN. So like I said, if something breaks, the users let us know immediately because they are doing it. I can't say speak to the volume. Kirsten or somebody could speak to the volume of that usage, but everything's in place, ready to go, and it's just a question of adoption.
Okay, well, I think we need to move on, but thank you very much for your presentation, Jim.
You're welcome.
Chris, I'm going to pass the screen share to you.
All righty.
And you may begin whenever you are ready.
Yes, let me cue this up. Oh, wait, hang on one second. Get to the share part here. Right. And hopefully everybody's seen that. So my name again is Chris Lenhardt, and I'm with the Renaissance Computing Institute, which is a research institute here at the University of North Carolina, Chapel Hill. And thanks to everybody for hanging in there on this holiday and taking you away from chili cook-offs and 5K runs and all kinds of interesting things, I'm sure. But just a quick word about RENCI, and actually, Jim, you provided a great segue there talking about cyber infrastructure science, because at RENCI we like to think that we work on the science of cyber infrastructure, in particular looking at the data science aspects of it, and with a goal of bringing sort of advanced technology to bear on various pressing problems, both of a science research nature and of a societal nature. And for those of you who don't know me, I've been working in earth and environmental data management for most of my career, and focused here at RENCI on those kinds of issues from the data science side, and have been involved with various projects along the way, including EarthCube and a few pieces of EarthCube. And I have to today do something that a high school English teacher told me never to do, which is to start off with an apology. And I routinely violate that. But my apology here is a bit of a bait and switch. The nominal title was to look about synthesizing, or to talk about synthesizing related efforts for cyber infrastructure of the physical sciences. And I had a really hard time with that topic. And so I'm going to do some synthesis here, but my goal in doing the synthesis is to put an idea out on the table for us to talk about for a potential activity to help to foster the synthesis that we're after in terms of developing an internet of samples. And so what I'd like to do today, just to outline the presentation, is to reiterate some context, some background that probably most of us are fairly familiar with, talk a little bit about some trends, some cyber infrastructure trends, and then to make my pitch. And then hopefully we can maybe chat about that a little bit at the end. Right screen here. So for context, we're well aware of the challenges that we're facing related to samples and building the Internet of Samples, and it ranges from the actual management of those physical items. I grabbed the screenshot from that report that came out a few years ago that we bring up periodically, and then on to the digital side, where we have the challenge of linking these samples and their data, and we're well aware of those kinds of issues of naming and unique identifiers and all that good stuff. And let me just go into that a little bit more and reiterate some things that came out of this effort, this add-on effort we had, or Kirsten had to IEDA, I believe it was, which was to delve into whether we could come up with a digital environment for sample curation. This was this so-called DESK project. And I just want to pull a few items from that report. And I think we mentioned this report at the first iSamples workshop. And I don't know if we were going to make that available, but we certainly can if that's of interest and of use. But the DESK effort had a workshop and had a survey. And from that, in the report, we distilled out a few things. Some being some high-level kinds of themes related to sample curation. Again, things we're pretty familiar with and well aware of, which is administration and curation of the actual samples themselves, what kinds of user functionality is needed in terms of, say, checking in and checking out samples, those kinds of services, what kinds of technical support you might need to offer in the context of a sample curation environment. And further, the survey was, we were able to distill some sort of higher level or first order curation functionality, things like assigning identifiers, obviously for the samples and the subsamples, being able to do batch modes and bulk modes and things like that. How can we link the system, say, from a repository system to a museum system, harmonizing metadata, something we're working on in the iSamples RCM. Also think about functionality related to collecting metrics for these systems. What kinds of, how well is the system operating? How many samples are going in, how many samples are going out? Can we come up with impact metrics and things like that? Another high-level functionality that would be a requirement would be user account management. Another notion that came up was, well, user account management is creating and managing accounts, assigning roles, and so on. And then the idea was also put forward about having users be able to have their own workspace. And some of this is built into various systems, but again, can we think of a more unified approach? And then also you have the idea of workflows. So you have the functionality, how do you put them together, what goes into the functionality in terms of actually doing the things. So again, maintenance of your catalog for your collection, administering or the administration of the collection itself, linking to other data, managing users. An idea too of, can you come up with a customized interface, user interface, and so on. And finally, again, technical support, how you support users at various stages in the process in the workflow. So, we have can distill up from this a number of big themes here, and my point in this graphic with these themes is that they keep coming up over and over again, and I'm going to ask a question later about these themes, the curation, the management, sharing, integrating data, digitization, data rescue, and these various cross-domain challenges. So just a quick segue here, or to tie it back to cyber infrastructure, I want to point out some trends which we're well aware of, and again, thanks to Jim, because in his conclusion they're kind of hinting at that cyber infrastructure and science go hand in hand, and we have lots of other things going on out there that may bear on the challenges we're facing in developing the Internet of Samples. So, for example, increasingly scientists need to access computation beyond what's available in their desktop. And how you deal with that in terms of the data, moving the data to the computation or vice versa. You have a lot more distributed data access and integration going on, and think of your Python scripts, your MATLAB scripts, your web services, and so on to grab parts of data and bring analysis and integrate data, and even starting to think about models of distributed data management. And in this context, I would point to, if any of you saw the recent announcement that came out of the National Oceanic and Atmospheric Administration. They have this big data alliance or big data partnership that they've developed as an experiment to test ways of getting NOAA data out and used in various ways. And they just released, I believe it was into the Amazon cloud, Amazon being one of the partners of the 5, the whole archive of NexRad radar data, which is precipitation data, and something like 2.6 or 2.7 terabytes of data uncompressed that are now out on the cloud, changing their data management model because the data used to be available. It still was available, but it was only available on tape or in a nearline way. So, are these kinds of things that bear on our challenges here. And then, I know that images are a part of samples, but you have increasingly advanced kinds of techniques, including high resolution. There was a great article in the New York Times not too long ago about, I believe it was a natural science museum in Germany that's doing high resolution, three-dimensional scans of all its holdings because they're quite fragile and they want to get them used, but it's wear and tear on the objects themselves. So that becomes another piece of the puzzle to be thinking about synthesizing in this context. So here's the setup for my pitch. And my question is, we have all this stuff we've been working on, these various themes and things that I outlined at the beginning. My question is, have we made any progress? And my point here is, by this graphic, is hopefully not to offend anybody, to imply that we haven't made a lot of progress, but really to suggest that there's a lot of challenges that get in the way of progress, that make it incremental and hard to do. And that will lead me to my pitch here, which is to say, can we try something new or something different, which would leverage some of our experience in cyber infrastructure and so on. And what I'm drawing on for this is something that we did here at RENCI. We helped, we didn't do it at RENCI, but it was a project that we worked with the National Center for Ecological Analysis and Synthesis, and we ran an Open Science Code Fest about a year ago. And this was a very fun, interesting, successful activity that after about 2.5 days had some really great outputs and really moved some things forward. So, you know, we have the workshop model, which we're quite familiar with, and we have other kinds of, you know, not binary, but bilateral connections, project to project, where we'll make progress. But this offers a potential alternate scenario. And how did our Code Fest work? The way we approached it, so first of all, it was an unconference style. But one of the things that we did that I think helped a lot was we didn't just walk into the conference the first day and start with a blank slate. We asked participants to seed the effort with ideas and to submit ideas through a website and using GitHub to propose topics, to start getting feedback, to start iterating on that prior to the actual Code Fest. And then at Code Fest, we kind of had a sort of a sprint mentality where we start off in plenary and put some topics out there. People would present them and help people understand better what they were after, and then there'd be some mingling, and then folks would vote with their feet and go off and work on the various topics. And then you'd come back in plenary, present progress, and then go back out and have another sprint, as it were. And, you know, the beauty of the unconference, it was totally participant-driven, facilitated by the organizing committee, but participant-driven, that allowed things to evolve organically, so that if stuff needed to be merged or split off, that could happen. If something didn't have enough interest, it would kind of die on the vine, as it were, or at least to sort of go into a hibernation mode, could be picked up at another time. But that's what worked in this context. So what were some of the outcomes? As I alluded, there was a lot of interesting stuff going on. We had at least one published paper come out of it, various improvements or enhancements in data integration code, some refactoring of hydrologic model. I think there was a couple games that were being worked on, and a couple other scenarios like feeding into requirements and tool development for some other major projects. So in my opinion, on balance, it was very successful. So why did it work so well? For a number of different reasons. One factor I would highlight is that we had a very diverse set of participants that had a lot of different backgrounds, both domain and technical backgrounds. We had a nice mix of experienced people who had a lot of experience with unconference, as well as new people such as myself who had never done this particular thing before, in addition to not being a coder. And then we had a very engaged, if I may say so, since I was on it, organizing committee that worked really hard to engage folks and have it all work out. And another thing that made it work well, I think, was a nice set of sponsors. So it was not just sort of the usual suspects like the projects or NSF, but we had our Open Science, we had Mozilla Science Lab also engaged. Another thing that was very useful was relying on social cyber infrastructure such as GitHub and Twitter, Etherpad, and so on as a means to do the knowledge management, the knowledge capture, the knowledge dissemination. And of course, we also still had the fallback of good old, you know, Post-it notepads, but those would be, you know, people would take pictures of them and then post them into the digital environment. And all this working together, plus it was in Santa Barbara, which didn't hurt either, helped with facilitating outcomes. So here comes the rest of my pitch. In addition to sort of the usual suspects in the iSamples context, you know, I'm wondering whether there's other partners that we might want to reach out to who are doing interesting things related to earth and environmental science research that we might be able to leverage in the context of doing an iSamples Code Fest. And I just put these folks on the screen here because they're projects that I have some familiarity with, whether it's Data One, which I'm sure people know about, DFC, which is run here at UNC, which is doing some interesting things with files and file management using iRods under the back end. We're working with the iPlant Collaborative to genericize their discovery environment, which gives you access to not only data management, but compute and other kinds of application layers. So maybe by bringing in a diverse group, not just the usual suspects, it might be something to consider if we wanted to pursue this. So with that, I will conclude my pitch and see what folks' reaction is and thoughts, and maybe we can think about doing something like this.
Thank you very much, Chris. I implore you all that if you have questions, please do put them in the chat box. Chris, can you talk a little bit about whether you have an initial idea of maybe what the topic of this Code Fest could be, or you know, you made a pretty long list of desired components. Are there any low-hanging fruits? Is it the whole, you know, topic that would be part of the Code Fest, or is that decided on the fly there?
Yeah, the basic premise would be it would be decided on by the people who are interested in participating. I think, you know, certainly, you know, while I said we left it up to the participants, the organizing committee had a vested interest in putting some things out there for consideration. So, you know, we, as it were, seeded things a bit to help with that. So in the context of iSamples, for example, we could, I would argue, just as a starting point, think about drawing on the working group, some of the working group activities. So, you know, I know the one working group I'm engaged with, which is the metadata one, working group one, there would probably be some topics there that could lend themselves to some focused and intense work in the context of a Code Fest or an unconference. And I'm sure some of the other committees, you know, there's some other silos that are trying to be broken down. We could take some of the pieces of the desk notion coming out of the desk environment to try to work on. So, you know, we can leave it open, but you don't want to leave it to chance. So you want to steer things a little bit.
So there's a question in the chat box about what is the benefit of having participation from non-coding domain scientists and educators, primarily for, in the case of Ben, faculty at an undergraduate institution?
That's a good question. So let me try to answer it. So I think the first order would, you know, having the domain scientists participate is important because they help drive the requirements. The other thing I would say, just sort of anecdotally, based on my own experience, not being a coder, I'm a data management guy, going to a Code Fest, you know, I'm sort of saying, well, what am I doing here? And the benefit of this was it wasn't all coding, right? So the activity I got engaged with was writing a paper that ultimately was published on the Dow of open science and for ecological research. And, you know, I had a minor role in that, but that's what, besides helping to facilitate the meeting, it was useful from that standpoint. And there's any number of other activities that could be promoted in the context to help engage educators, you know, if they're going to do a game or something like that. You could have a domain scientist with educators, with coders to develop a game, for example.
So there's another question in the chat box about what about having organizations attend who wish to develop a guided needs assessment for this type of work at their specific institution? Yeah, I mean, again, without wanting to make it sound like a trite answer, the answer is whatever people want to work on, you put it into the mix, put it into the hopper, and, you know, again, if you can do it ahead of time in the sense of putting that out there and then trying to do some networking or engage folks who might be interested in it to show up and then carry it forward, that way you help ensure that idea would not, you know, that would gain some traction in the context of the actual unconference itself. So there's lots of opportunities to pitch an idea and to market it and to get some momentum behind it. So it's not just put it out there and keep your fingers crossed and hope it flies. So yeah, by all means, if there was folks who wanted to work on a needs assessment to help institutions assess their need for repository management for physical objects, yeah, that'd be great. Thank you very much, Chris. Well, I think it's time to, oh, wait, we have another question. Could we consider this Code Fest for the next iSamples workshop, even if the main topic will have to be the shared vision of the Internet of Samples?
Good question, and I pondered that in the context of thinking about pitching this idea. And we could, I mean, it's not out of the realm of possibility. I think we'd want to think hard about that in the sense that we'd want to make sure we had the right length of time, that we engaged the right people. And my question in those sorts of contexts would be, do we have enough time to do that given that the workshop is going to be in a couple months? My suggestion would be, or my thought was, that we could maybe use the workshop, a session or a breakout, to explore the idea more fully and think about it more fully. Just as a point of information, if I remember correctly, the cost of the work of this Code Fest was a bit more because a lot of there was no registration fee. I mean, you had to pay to get there and to pay your hotel and whatnot. But and you need a lot of rooms. Whatever venue you have, you tend to need a lot of rooms, and sort of you got to make sure you have the right kind of infrastructure. So I think we'd want to think it through a little bit, and I'm not sure we could pull that off by January.
Okay, great questions, everyone. I think it is probably time to adjourn, but thank you to Jim and to Chris for those very interesting presentations. These webinars will be archived on the iSamples YouTube channel and linked on the iSamples website for future viewing. Please join us for our next webinar, which will be on Wednesday, December 2nd at 4 p.m. Eastern Time. Have a nice day, everybody.
Thank you very much.